Okay, good morning, everyone. Today we'll get into the fun stuff, the good stuff. This is chapter 5, AC analysis. This is where we spend a lot of our time, and I also like to do a lot of in-class problem solving. If you recall, at the beginning of the quarter, I stated that we use complex numbers and complex math to solve our circuit problems for AC analysis. And so there is a worksheet on the website, on the Canvas website, and several students have been working with that worksheet. But if you have not yet done so, please go ahead and do so at your earliest convenience. Otherwise, this entire chapter, actually the rest of the class, is going to be, well, very difficult to catch up. Okay, so students need to be adept at performing complex number math on their own calculator devices. So having said that, let's bring up the class notebook. And let's go to section 02. There you go. Yep. And chapter 5. Okay, sinusoidal analysis. This is also known as sinusoidal steady state analysis because the primary signal of the function we look at is sinusoidal in nature. And I will explain that in just a couple of slides. So what we will study in this chapter is basically the response of inductors, capacitors, and resistors, the three components, the response of these three components to an applied AC signal. When I say AC signal, it could be an AC voltage or AC current. Okay, so we will study how AC circuits work compared with DC, and how can we mathematically model the relationships between the voltage and current quantities for all these three components. Okay, so most of the chapter is not about new analysis technique. Okay, the analysis techniques are exactly the same as what we studied in chapters 1 and 2. No different. It's KVL, KCL, Ohm's law, everything just works as we learned earlier, right? They're all based on laws of physics. Those are permanent in nature. They are not, they are not arbitrary. So they apply equally whether a circuit is DC source or an AC source. Okay, so when we state AC circuit, it simply means that there is a source which has alternating current capabilities, meaning the value of the voltage or current of that source is not fixed or constant with respect to time. So the circuit by itself is made of the same components, R, L, and C. That doesn't change. The only thing that changes is the source is now AC versus DC. DC, it was a flat line. AC, the value changes. And so we'll see how everything functions in these AC circuits. So here's an example of typical sinusoidal AC waveforms. Actually, not sinusoidal, all kinds of AC waveforms. So AC, actually DC, if plotted with respect to time, whether it's voltage or current, has a fixed value, right? So it's a flat line. It's a completely flat line. That's what we have studied so far. Doesn't change with respect to time. AC, on the other hand, if you plot the values of alternating current, could have any random value. As long as the value is not fixed with respect to time, then we say it's an AC waveform. And typically, the signals of the waveforms we look at, they are repeating in nature. Okay, especially the ones that we generate using like a function generator or a power supply generator, then those are repeating in nature. Okay, so based on the shape of the waveform, based on the value of the waveform, we plot it out in the shape of the waveform. We can have multiple different kinds: triangular, square, ramp, sawtooth, rectangular pulse. The one that we will study is basically here. It is known as a sinusoidal waveform. Hence, the title of this chapter is also sinusoidal analysis. Okay, so it's AC analysis or sinusoidal analysis. When we say AC, it means any kind of waveform. When we say sinusoidal, it simply means the waveform at the top. Mathematically, it is represented with the function sine and cosine. Sine and cosine. So sine x and cos x. That's what we'll use mathematically. Okay, mathematical representations. And then, of course, the quantity can be any of the three standard quantities: voltage, current, or power. All three of them can be described as functions of time. So again, we saw a little bit of that in chapter 3 when we did piecewise linear analysis. We had a triangular wave in there. We had a square wave in there. The values of those waves or those functions were not fixed with respect to time. So we used the we used the graphical representation and described it as straight lines by dividing it up into pieces, right? So that is one way of mathematically describing these functions. Sinusoidal waveforms, straight up, we can simply use sine x and cos x. So the sine wave representation is provided by this equation right here. And if you think of this in general terms, x of t is xm cos of omega t plus or minus theta, or say plus theta. Okay, and x can be either voltage, current, or power. In this case, I'm using voltage to make this illustration for this equation. But this equation applies equally to either current or even power. Okay. Typically, we will look at signals which have just voltage and current. So V of t and I of t. Now, there are three separate quantities inside this mathematical equation. And there is a reason we keep all three of them separate. Let's look at the first one. And we'll look at all three of these separately also in the next few slides. The first one describes the magnitude or the amplitude or the peak value of this waveform. Okay, the subscript m comes from magnitude. Typically, you would also see VP or IP. Okay, so VM would be equal to VP. P stands for peak. It's basically the value of the waveform on the y-axis. Okay, value of the waveform on the y-axis. So in the waveforms, it's always plotted with respect to time. So it's always time on the x-axis, right? We say V of t or I of t. So the voltage or current as a function of time, meaning what is the value of this voltage or current at any given point in time. And so this mathematical expression describes that value. So Vm is the same as Vp. We can also write Im, magnitude of the current. That is also the same as IP. These are the values of the waveforms on the y-axis. So y-axis values. Okay. Y-axis values. Omega describes the angular frequency. Typically, our waveforms would have frequency. And again, as I said, we'll look at all of these quantities in detail in the next few slides. And omega is the angular frequency or angular velocity in radians per second. And then finally, the third quantity is phase. Okay, the phase is kept separate from the frequency, and phase is described in degrees, not in radians. We can, of course, combine them by converting degrees to radians and vice versa, but we keep it separate for a purpose. Again, mathematical purposes. And so we will see that in the next few slides. Okay, so these are the three quantities that we need to be aware of. Then the overarching units for all three, the individual units for all three are separate, but the overarching unit for this function would simply be what that quantity is. So if it's V of t, then it would be volts. If it's I of t, it would be amps. Okay, it doesn't matter that there are three independent quantities in there. You're describing the function. The equation is describing a specific quantity. So the units for that equation would be the quantity that it is describing. Omega, the angular velocity, is also given by the equation 2 pi f. F is 1 over t, that is the time period in seconds. Okay, t is the time period in seconds. And then one mathematical expression we need to keep in mind is this one. Sine x is cos of x minus 90. Sine x is cos of x minus 90. Okay. So this is just an introduction of the mathematical representation of a sinusoidal waveform. This entire chapter mostly is about learning the math techniques or mathematical techniques that would be required to solve for AC circuits. Okay, the equations remain the same, they don't change. So let's look at what magnitude or amplitude or peak value is. Okay, as I said, okay, question being asked in the chat. So again, if online students have a question, please feel free to speak up. You can interrupt. It's absolutely fine because I will not be able to monitor the chat window. So again, question being asked is what type of waveform do American power sockets use? Well, that's a good question. I typically do bring up. It's a general knowledge question. So what is the power outlet rating? Online students and in person. And I stated this on the first day of class. Some murmurs of about 100 approximately. So in North America, it's 110 or 120 volts. And frequency, anybody? 60 hertz. Outside of North America, it's anywhere between 220 to 240 volts and 50 hertz frequency. So this goes back to the war of current that took place between Tesla and Edison. And for that, I have to go back to chapter 1. So let's do the segue. Let's go to chapter 1 and look at this. Because of the holiday this quarter, I skipped over this slide. Okay, how many of you are aware of this? The current war or war of current. There's actually a movie that came about, I don't know, more than 3 or 4 years ago. Nicholas Hoult and I would say Benedict Cumberbatch, but I'm not sure. Anyway, it's about the competing technologies of AC versus DC. This is in the early days of electricity generation, power generation, right? So Edison already was an established, established researcher, businessman, who was conducting research into many things. One of the things he was doing research in was DC power generation. So at that same time, and this is the late 1800s, Tesla was I want to say Serbia, but actually I don't know. He was born in a region which is now in Serbia, I think. Anyway, he was in Europe. He was conducting research mostly about alternating current and transformers in power generation for AC. Edison at the time had some kind of unsolvable problem, and Tesla came over from Europe to work for Edison in his factories. And apparently Tesla did solve that problem. If y'all don't know, historical accounts point to Tesla being a very, high-level mathematical genius. He could do theoretical sums and visualize a problem or a solution inside his head. And Edison, by all accounts, was a jerk, as many people and many powerful businessmen are. And Tesla was able to solve that problem. That problem had a bounty of about $100,000 on it. And so when Edison, Tesla said, I solved your problem, please give me my prize. And Edison apparently laughed in his face and says he was just joking about it. You are my employee, and you're not going to get any additional money. I don't know whether that's true or not. Obviously, none of us were alive at that time, but that's what some historical anecdotes state. Anyway, they had a falling out between the two of them. There was a big falling out, and Edison either fired him or Tesla left shortly thereafter. So Tesla was working on AC and Edison was working on DC technologies at the time that they had a falling out. And from that point on, Edison did all in his power to actually denigrate Tesla and denigrate his work. So what he would do is he would put up like street shows where people hired by him, anonymous people hired by him, would electrocute animals in the street, showing that, you know, AC is dangerous. But what he wouldn't tell people is like the AC would be like very high, hundreds of volts. And he would show his DC technology with the lower voltage, like, you know, 50 volts or 100 volts or something like that. And he would show that DC is safer, AC is, you know, very dangerous. And again, this is the early days, right? If you have never seen electricity, all you've been used to is like oil lamps or gas lamps. This is like a wondrous thing, right? You have electricity coming in, but it's dangerous. You see sparks everywhere, people being electrocuted, which happen in real life. And so that point on, they were just kind of in a war. They were competing against each other. They're bidding on these electrification projects. And then it all came to a head during the World's Fair in Chicago in 1880s. Can't remember where it is. Somewhere 1880s or 1890s. And Edison had the backing of Westinghouse, which is still a brand name that's in existence today. And Westinghouse put in some money to back Tesla. Sorry, not Edison, Tesla. And Edison had his own company, Edison Electric, which you now know as General Electric, GE. And they were competing on this World's Fair. Tesla's bid came in $100,000 cheaper. They won the contract and they electrified the entire fair safely and effectively. And then from that point on, AC just kind of like took off. One of the world's first power stations was set up near Niagara Falls. I think it was still in existence and supplying electricity until just recently. And this chose a nice, safe, round number of 100 volts. And that 100 volts somewhere along the way become 110 and then now 120. And so that's the reason why North America uses 110, 120 volts. The world over came later on. If you think about it, the technical reason is P equals IV. So if you wish to transfer a lot of power, you can increase either the voltage or you can increase the current. But the power loss is square of the current, I square times R. So the more you increase the current, the more power you lose during the transmission. We are talking about transmitting over hundreds of miles. So transmission power losses are huge. So you want to keep the current low and you want to keep the voltage high. So the higher the voltage, the more power you can transmit with fewer losses, so more efficiency, so cheaper to do so. So the rest of the world that followed later has a higher voltage rating, 220, 240 volts. In North America, it's 110 to 120 volts. That's one of the reasons. Anyway, so go ahead and check out the movie if you have time. Check out, well, there are several articles about this war that went on during that time. Many of the technologies that we use nowadays can be attributed to Tesla. Edison, by all accounts, was not he was more kind of a learn by doing guy. He would not take the time to mathematically solve out anything because apparently he was not so good at it. And so he would just start doing stuff, right? He would make an iteration. So you have heard the famous story about the light bulb, right? They say he made so many light bulbs before he could get an actual working one. Well, that's the reason why. Don't know if that's true or not, but that's the general narrative. Whereas Tesla would take time, work out the theory first, and then, work on the practical solution. Anyway, so DC and AC, that's kind of a little bit of the history in a very brief talk. So most of the technologies that we use now, the electric motor, the transformers, there's lots of people who did research on this. Transformers, there were three, I want to say Hungarian researchers who came up with the primary theory governing mutual inductance. And again, research is done by like hundreds of thousands of people all across the world. It's someone who takes it all together and puts it into a usable form or markets it that becomes very famous and associated with it, right? So Tesla did invent a lot of the technologies or did a lot of research in the technologies that we use today. So the electric motor that we run today, and that's why, that electric car company named after Tesla. The wireless charging systems that we use in your smartphones and your devices That's basically concept of mutual inductance. That's based on the Tesla coil. And so he actually had an idea where he could actually broadcast free power in the air. It would be true wireless. You would not ever need to plug anything into a wall socket. You would just absorb energy from the air. And he had something like this set up in somewhere in New York City, Staten Island or Long Island, Staten Island, I think. Anyway, let's get back to our talk. So amplitude, magnitude, or peak, right? That's the value on the y-axis of the quantity that we're describing. For waveform 1, it is 0.5. For waveform 2, it is 1. And waveform 3, it is 2. Simply describes the quantity value on the y-axis. That's all it is describing. If you note, it is only describing one end, one direction of that waveform. It's not describing the second direction. Okay. So when we read Vm or Vp, it is describing both the positive as well as the negative peak. Okay, it is describing both the positive as well as the negative peak. This is the waveform that comes out of our power outlets. It goes from 0 to a positive number, back to 0, goes to a negative number, then comes up back to back to 0. So we state this as the positive half cycle and this is the negative half cycle. Okay, positive and negative half cycle. And the Vm or V peak describes both. So if you actually wish to describe the complete waveform, you would use a term called P dash P. It'll be 2 times Vp or 2 times Vm. I want to note that most books would use a subscript of P for peak, but the system that I'm using, the book that I'm using, uses M for magnitude, but they're the exact same thing. So students should be aware of both. So if you see Vp or Ip, it is referring to Vm or Im. Okay, magnitude or amplitude or peak stands for the exact same thing. They're all synonyms of each other in this instance. P dash P is peak to peak. Okay, peak to peak. All right, then, no, we look at frequency. So what is frequency? I think I jumped ahead by using the word cycle. So I just said, right, waveform goes from 0 to positive, positive, back to 0, from 0 to negative, and from negative back to 0. So a waveform starts off at 0. Oh, that's weird. It starts off at 0, goes to a positive peak, comes back down to 0, goes to a negative peak, comes back up to 0. When it traverses both the positive and the negative peaks and comes back to 0, we say it has completed one full cycle. This is one full cycle. Okay, one full cycle. This is also mathematically represented by the uppercase T and is known as the time period of the waveform. Time period or just period of the waveform. Okay. Lowercase t is the variable, right? Function of time. Uppercase T stands for the time period of that waveform. This is important. We said about 60 hertz, right? for the North American power outlet. So what exactly is 60 hertz? Well, it's the number of cycles that a waveform accomplishes or goes through in 1 second. So frequency F is the number of cycles in 1 second. It's named after the German physicist Hertz. So unit is Hertz, but short form is always used Hz. Hz. And the relationship between frequency and time period is they are inverse of each other. Frequency is 1/t. So now frequency is the number of cycles in 1 second. So you would think it's, North American outlet is 60 hertz, meaning it goes up, it goes down, it goes up, goes down 60 times in 1 second. That seems very fast, right? Anybody ever get zapped or shocked? Right? You feel a zing. The reason you feel a zing is because it's going up and down, meaning it's changing. The electrons are moving back and forth, right? It's not a pleasant experience. I mean, there's a shock that goes to the body. But if it's DC, I've never experienced a DC electrocution, but DC, what I've read is that you get stuck because the value is constant. AC, it goes back and forth, meaning the value does go to zero. It's 60 times in 1 second, but it does go to zero at some point in time, right? And so that's the reason you might be actually thrown off. So if it's low enough voltage, if it's just 100 or 110 volts, you might be able to get thrown off. But if it's DC, you would just get stuck. That's what I've read. One other thing is 60 hertz seems like a lot, but it's actually a very, very, very low frequency. Okay, most people would not even be able to hear 60 hertz. People like me, whose hearing is almost due to, well, lots of loudspeakers and headphones during our youth. As you get older, you can't even hear at the extreme range of the frequency. But normal human range is 20 hertz to 20 kilohertz, right? 20 hertz to 20 kilohertz. So 60 hertz is a very, very, very low range. 20 kilohertz is kind of like the maximum. Very few people can probably even hear that high. Most of us would be around 15, 16, 17 kilohertz. 15,000 hertz. Even that is not considered a high frequency. Okay, some of the typical values of the frequencies that we see in signals around us. Let's take AM and FM radio. AM is amplitude modulation. You have the number of a station or the name call sign of a station. It says 680 AM. That 680 AM technically stands for 680 kilohertz of frequency. That is the broadcast frequency of that radio station. 101.7 FM stands for 101.7 megahertz, 10⁶. That is the broadcasting frequency of that radio station and also the call sign. Mobile signals, satellite signals, wireless routers, 2.4 gigahertz, 5 gigahertz. Very high numbers, 10⁹. So these are just the common frequency signals that are all around us in everyday life. Okay, so 60 hertz is very low. And then finally, we have phase. Phase is basically the point in time at which a signal arrives or crosses the y-axis. Okay. We could also say is the point in time when it crosses, or the distance away from the y-axis when it crosses the x-axis. Let's explain. You have three waveforms, 1, 2, and 3. Let's call this 1, 2, and 3. Waveform 1, actually, let's look at waveform 2. Waveform 2 crosses the x-axis right here when time t equals 0. This is the point we begin our analysis, right? So waveform 2 crosses the x-axis right here when time t equals 0. If you look at the chart of the waveform, what do you see? Time here, and ignore this pi. This is time, okay? So mathematical conveniences, so ignore that. This is time on the x-axis. These are positive numbers. These are negative numbers, right? Standard mathematical or graphical representation. So if time is 0 at the point at which we begin our analysis, what are positive numbers? +1, +2, +3, +4, future. Minus numbers on the left are the past. If you're analyzing at t = 0, minus numbers mean time has already gone by. Does that make sense to everyone? Right? So on the right, you have the future. On the left, you have the past. Now, if you look at waveform blue, waveform number 3, waveform number 3 has already crossed x-axis sometime in the past, right? It's crossing over the x-axis sometime in the past. So it's ahead of waveform number 2. So it has a positive phase with respect to waveform number 2, or with respect to time t = 0. So our reference point would be time t = 0 in waveform number 2, which is the waveform in blue has already crossed the x-axis sometime in the past. And we represent that by a positive phase. On the other hand, the waveform in red is arriving, has not yet arrived, and is crossing the x-axis at a later point in time. And so we say that waveform lags. So this leads, this lags. And that lagging is noted by a negative number. And we keep it separate. We keep it separate. We don't add it to the frequency because we want to represent it mathematically as a vector. Okay, so we keep it separate. That is the reason why we keep it in degrees and not convert it into radians. So these are the three quantities. We have magnitude, we have frequency, and we have phase. We work with these three quantities. Yes. That is correct. Yes. Amplitude should be 1. So that should be 1. Good noticing. All right. Pause and questions. Okay. All right. Moving on. So what is the average of this waveform? You have half of the cycle in positive, half of the cycle is negative. What is the average value of this waveform? Elementary school math. I heard some murmurings, but it's 0, right? So if you're trying to describe the average value or mathematically trying to perform any calculations and you try to represent as an average, it's 0, doesn't work, right? Yet energy is still being transferred. Value of the voltage or the current is not 0, it is still being transferred. But they needed a way to mathematically describe this value. Think of it in this terms. If these were mountains of dirt and you flatten them out completely, what would be the value of that waveform or the equivalent DC value of that waveform? So even though right now we can say this is plus and minus, if you add them together, it becomes 0, that's not fully the case. If they were all positive peaks, let's say you flip the positive peak, flip the negative peak, and you had a waveform like this, and you flattened it out, what is the value of that waveform? Somewhere over here, approximately, right? So what they did was, it says we can't take the average of the waveform. So what we will do is we will first square the waveform. We'll take the square of the waveform, then we will take the average. And because we took the square, and then now we are taking the average, at the end of our result, we will take the square root. Okay? So they came up with a term known as root mean square. Mean, of course, is another word for average. It literally means that value is the square root of the average of the square of that waveform. And we are talking about the y-axis. Okay, we're talking about the y-axis value, never the time. Okay, so that's more popularly known by its RMS value. Sorry, more popularly known by its acronym called RMS. RMS. But RMS stands for root mean square. It literally is the square root of the mean of the square of the waveform. RMS. So here you see it. We have v of t, the function. Mathematically, we square that function. We square the function, then we take the average. Taking the average means summing it up over one single time period. You sum it up, or one integration is just summing up all the individual slices. So 0 to t, add up all the individual slices, integrate from 0 to t, take the average, divide by t, which is right here, 1 over t, and then finally you take the square root, which is right here. Hence, root mean square. Okay, root mean square. So the average power transmitted to a circuit, to a resistor, for let's say, would be given by the RMS values. Okay, it'd be given by the RMS values. So average power is V square over R. The V value would be the RMS value. So V RMS square over R. Same thing for current. It would be I RMS square times R. As I stated, the equations do not change. The equations remain the same. P is the product of voltage and current. P is V times I. If you are transmitting AC voltage or AC current to a resistor, you use the average value. In this case, it's the RMS value. The RMS value, V square RMS, or V RMS square over R, I RMS square times R. When you solve this equation for sinusoidal waveforms, meaning you plug in V of t as sine x or sine t, and you solve it, there's a derivation. If you wish, you can stop by my office. I'll go over the derivation with you. It's nothing too strenuous, 4 or 5 steps. The relationship you obtain gives you the RMS value is the magnitude or the peak value divided by root 2. Okay. For instance, Vm would be root 2 times VRMS. Vp or Vm is root 2 times RMS. Peak values will always be higher, right? Peak numbers would always be higher because we are talking about average. So if you think about this waveform, right, these are peak values. And this would be the RMS. The peak numbers would always be higher. So this is for only sinusoidal waveforms, not for anything else. Only for sinusoidal waveforms, the relationship is VRMS is the magnitude divided by root 2, or the magnitude is root 2 times VRMS, RMS values. So then I would ask you the question and take a wild guess. What value are we talking about when we refer to our power outlet as 120 volts? Is it peak or is it RMS? RMS is one single value. Peak value just describes one moment in time. So if we state one single value for our power outlets, RMS, absolutely, it's RMS, always RMS. All meters, everything that you use to measure the voltage or current will always give you the answer in RMS, never peak. If you're taking the lab 5 this week is about, first one for AC analysis where you use the sine waves, you'll see it on the oscilloscope. The oscilloscope is a very powerful measurement instrument. It allows you to see the waveforms, the shape of the waveform, and take multiple measurements. And you can see the shape of the waveform in an oscilloscope. But other than that, if you wish to actually measure the actual voltage or actual current, it's always in RMS. Okay, one single value only describes one average value. That's all it's describing. So why do we work with sinusoidal analysis? Why is sinusoidal so popular? Well, sinusoidal voltages and currents are easy to generate. Basically, it goes off in a circle. So there's a turbine. The turbine has a electric coil rotating in a permanent magnetic field. That rotation is mechanical movement. It could be due to hydropower, water, or it could be due to wind turbines. And that rotates, that mechanically rotates that coil inside that magnetic field, and that generates, going into physics, electromagnetism, that rotating coil in a magnetic field generates generates movements of electrons, go up, down, up, down, up, down, because of the magnetic poles of that magnetic field. So it goes north, south, north, south. So it's rotating north, south, north, south. And that's how you actually generate a sinusoidal waveform. So it's very easy to generate. They're easy to transmit over long distances because of transformers. Okay, transformers are basically mutual inductance, two inductive coils wrapped around a solid magnetic core. It's not Optimus Prime. It's just two inductive coils wrapped around a magnetic core. And they easily allow you to step up the voltage or step it down, meaning increase the level of the voltage or decrease the level of the voltage. So when the voltage is generated at the power station, it's then stepped up to thousands of kilovolts, tens of thousands of kilovolts, and then it's transmitted over long distances. Remember what I said, long distance transmission is going to result in power loss. So when power loss happens, voltages and currents will be reduced. Okay, at the end of the receiving station, they are stepped down. So when they are stepped down, you are now bringing those values of the tens of thousands of volts down. And then they're distributed by using multiple transformers. Sometimes if you go down a residential street, you might see a cylindrical metallic cylinder wrapped around the electric pole. That is a transformer. What it is doing is it's taking the power supply line and distributing it out into 3 or 4 different areas. That's what it does. So again, it's easy to handle, it's easy to generate, it's easy to step it up and distribute. Mathematically, it is easy to handle sinusoids because the resulting value from a derivative of integral of sinusoid is the same. It's a sinusoidal shape. Sin x is cos x is sin x, right? Everything that we have seen so far, all the analysis that we have performed, it's time-based, so it's derivatives and integrals of the voltages and currents, right? And so if you take a mathematical derivative and integrals of sinusoids, they are also sinusoidal in nature, makes it easier for us. Even better than that is that the AC steady state voltage or current, again, we're only looking at steady state, not transients, can be easily represented as a vector. Okay, that's where the complex numbers comes in. Okay, we use the imaginary numbers for mathematical representation. So the math is easier. So instead of performing derivative, instead of performing derivation and integration, we can simply take our analysis techniques that we have learned in chapters 1 and 2 and just apply them to solve for AC circuits. That's it, as easy as that. And so we introduce the concept of phasors and impedances. Okay. These allow us, this mathematical transformation allows us to reduce differential equations into simple circuit analysis problems. We can apply all techniques that we have learned so far, but the only thing is all the quantities are mathematically vectors. Okay. They are complex quantities represented by complex numbers. Sources are represented as phasors, inductors and capacitors as impedances. Resistors behave exactly the same way for AC as they do for DC. So there is no change. Okay, resistors work exactly the same way. Inductors and capacitances, however, do not. Remember, they are energy storage devices, and the energy transfer takes some time. So in AC, you have positive and you have negative, meaning the energy is constantly flowing in and out of these energy storage devices. And so then we will see how we can actually mathematically model these. Sources are represented as phasors. These phasors are not the ones from Star Trek. They are not going to stun or kill you, but they will scramble your brains occasionally. So we see we have a time varying waveform represented by the sinusoidal waveform right here. Okay. And what we will do is we will represent this time varying waveform as a rotating vector in the complex plane. Okay, rotating vector in the complex plane. So time domain, in the time domain, we have three quantities, Vm, omega, and theta, right? If you think back just 2 slides ago, I said the generation of AC voltage or current is due to a circular rotation inside a magnetic field, goes between north and south pole, right? So this is kind of like the opposite of that. You're taking a sinusoidal waveform and you're representing it as a rotating vector in the complex plane. The rotation is counterclockwise, okay? But the phasor is simply a single snapshot. It's one single instant in time. The only thing it represents is basically the moment in time where it crosses, or the value on the y-axis, meaning the point in time where we begin our analysis. So it is simply one single snapshot at a single instant in time. Now, what does a vector need? What does a vector need to describe it? Magnitude and direction, length, and the angle it makes with the real axis. So we have the real axis on the x and imaginary on the y. Let's make this a little bit bigger. You only need two things: the length of the vector, which is given by Vm or Vp, and then you need the angle it makes with the x-axis. That angle is the phase of that waveform in degrees. And this is the reason why we keep it separate. This is the reason why we do not convert it into radians and combine it. Okay, Vm or Vp. So if you have a sinusoidal waveform, you simply take the magnitude and you take the phase. That's it. You only need two things to describe it. Nothing else. Only two things. Oh, out of time. And then that gives you the polar coordinates for this phasor. And so I'm going to draw a phasor like this, Vm, phase angle theta in degrees. The projection of this vector on the x, on the real axis, and on the imaginary axis gives you the rectangular coordinates or the Cartesian coordinates of this waveform. So you can represent this as A plus JB. In electrical engineering, the imaginary number is noted by the letter J and not I, because I is reserved for current. So that's a lot of concepts in here. There's also a homework that's due tomorrow. I'm going to take a look at that homework and see if there's something I haven't covered yet. But I think for the most part, you should be able to get started on that homework. So go ahead and get started, and then we'll pick up here again on Friday. Yes. It's just notation, JB.